Neighborhood functions, focal and block functions in ArcGIS. Neighborhood functions often go by other names depending on what discipline or subdiscipline of geomatics you're working in. So they might be called filters or filter functions, or under the more general name, convolutions. So those are alternate names for the same stuff that you're going to be learning in this module. So neighborhood functions or filters, particularly in remote sensing, we often call them filterings, and convolutions in general are sometimes used in GIS and also in the context of deep learning. So convolutional filters, or a convolution. So what is a neighborhood function? Well, we have two types of neighborhood functions. We'll look at case over here, case 1, and then case 2. Case 1 is called a block function. Both of these, case 1 and 2, use the same definition of a neighborhood. The neighborhood that we see here is a 4x4 block of cells. Or it's actually 6x6, 4, 5, 1, 2, 3, 4, 5. I'll put a 6 one there. And then down the side, 6. Like so. So that's called the neighborhood. Or focal filter, or focal. We won't call it focal filter right now. Just the neighborhood. And the neighborhood then is a block of cells. This block of cells is overlain on top of an existing raster. Here, A and B in case 1 simply show that we have a block of cells, one beside the other. So A and B are the same neighborhood, they're just juxtaposed and are adjacent to each other. Now, that neighborhood, in the case of 1, that panel, would then move to the next contiguous block of cells. So there would also be one coming up over here after that. And then down here, and then down here, and then down here, etc. over the entire raster image. What happens then is that something is done to the values in the underlying cells within the neighborhood. For example, maybe the maximum value is found. And then the maximum value within that block is assigned to each cell. So each cell would get the put a little m in there for maximum. Then, moving by one block length over from A to position B, again the same thing. The maximum value within each cell, or from all the cells, will be assigned to each cell. And then over to position C over here. Same thing. We would look inside that block or neighborhood, find the maximum value and assign it to each cell. And that would become the output raster. And these are called block neighborhoods because of that. Because each neighborhood contains an exclusive set of non-overlapping cells. And that function, or I should say the block itself, is moved across the entire raster, always assigning some summary value within each block to every cell within each block, and that then becomes the output raster. In the second case, on the right, we have what are called focal neighborhoods. Those are the most common. So focal functions. Focal functions also use neighborhoods, and they're called focal functions because each neighborhood has a focus cell. So for example, if I had a region like this and I had 5, 2, 1, 2, 3, 4, 5 by 5, 1, 2, 3, 4. The focal cell is the cell at the middle of the neighborhood right here. And then what happens as it visits a group of cells, like we see the yellow one, I'm just outlining it up here. It looks at all those cells and assigns some summary value only to the focal cell at the center right here. Unlike the block, where it would assign that summary value of all the cells within the block or neighborhood to all of the cells within the neighborhood, the focal functions only assign the value that summarizes all the cells to the central focal cell. So that's often, it could be an average, for example. So an average of all the cells then is assigned to the focal cell. And the blocks move not in, or I should say the neighborhoods move not in blocks, but on a per cell basis. So after the first cell, the next position then for the neighborhood is right over the next cell, right there. You can see the blue one. So it's moving over by one cell width instead of one block width, like you see in the block neighborhoods. And so the neighborhoods both contain overlapping cells, unlike with the block case. And again, that same summary value would be calculated for all the cells in position B, and that would be then assigned to the focal cell of the neighborhood. And then again, it would move over by one cell width. Didn't get that line too good. And this here would become the focal cell right in the middle. And then the summary value would be assigned to that cell. And that's how the output raster is created, like so, until all cells have been visited, even the ones along the edge, where you wouldn't have a full neighborhood anymore. So when visiting, for example, this cell here, you only have a half neighborhood, like so. And so this can induce edge effects. When using a focal neighborhood function, simply meaning that cells along the edge will not have a full neighborhood from which to draw a summary value to be assigned to the focal cell. Now, we have numerous types of neighborhoods that are possible. The most common is the rectangle. So that's the most common. Is a rectangular or square shape used in a focal neighborhood function. The circle is the second most common that's used. And then we have some special ones, like annulus and wedge. An annulus has a focal cell in the middle, and then it has a gap of cells that are not looked at in the computation, a gap of radius r. Call that radius r1. And then another radius from that cell, we call that r2. And only the values within r1 and r2, out here in red, are used in assigning a value to the focal cell in the middle right here. And so that's used for very specific types of circumstances. Often when you're looking at or researching things about scale effects or relationships between values at a distance, those analysis can be useful. We also have wedges, which is like that, where the focal cell is at the apex of that wedge right there. And this is used in that only cells in here will be used to assign the summary value to the focal cell. This is used in the context of things where you might have information about your data having some sort of direction, for example. Let's say, pollen dispersal. So some pollen is dispersed by insects, so entomophilous pollen, and then most, of course, for a large number of trees, like birch, for example, it's dispersed by wind. Pine as well, spruce, etc. And so maybe you're studying something to do with pollen concentrations or pollen effects in space, and so you might look at the source trees as being a wedge upstream of the major wind direction, and then a wedge neighborhood might make sense when you're trying to figure out dispersal patterns. It's one example. But generally, rectangle is the most frequently used, probably 99% of the time. When you're doing neighborhood functions, you're using a rectangle. Circles are even rare, and simply that's because you cannot get a perfect circle out of a raster without an infinitely small cell size. So let's look at a rectangular neighborhood to start. So here I have two rectangular neighborhoods, different sizes. I have what's called a 3x3 neighborhood right there, and that's the red neighborhood. The focal cell here is just in blue. It's part of the neighborhood, by the way. So the focal cell is included in any computations of summary values that would be assigned to the focal cell. If you didn't want it included, you'd have to use a nullus in this case, and have a reason to. Then if we include the green ones plus the red ones, right here, that's called a 5x5 neighborhood. Sometimes neighborhoods are referred to by the number of cells in them. This would be a 9-cell neighborhood. So a 9-cell neighborhood. And this would be a 25-cell neighborhood. So generally, if somebody's talking about a neighborhood as the number of cells, they're almost always exclusively referring to a square neighborhood. So always referring to a square neighborhood if you're just talking about the number of cells. So it's another way to talk about the neighborhoods is how many, you could say a square neighborhood with 9 cells. And you'll notice these are both odd numbers. If you don't choose odd numbers, then you could have a spatially biased estimate for whatever summary value you choose to compute within the neighborhood. For example, a 4x4 neighborhood, if that was possible. Let's look at an example here. I'll just draw, and I think I'll use bright yellow here. So let's just look at this, just ignoring the colors for now, and I do a 4x4. So again, ignoring the background colors here, where's my focal cell? Well, I don't have a exact focal cell. I'd have to choose something out of that center, and there's 4 of them. There's nothing in the middle. because I have a equal number of cells in X and Y. So when doing so, one of these would be chosen as the focal cell, either this one, and let's just say it was that one. Well, you can see right away then that you have a non-symmetrical neighborhood. Which means that you have more cells, in this case, in the northwest-ish quadrat, so all out here, in computing the focal value than you do on the other side. So you have 9 in one quadrat and 7 in the other. It's not really quadrats, but in the regions anyway. And so using a even number as the number of columns and rows for a square neighborhood leads to that type of a spatial bias computation, which to be avoided then is the reason we always choose odd numbers, because with odd numbers, we always have a cell right in the middle of the neighborhood. Here's an example of a circular neighborhood defined by a radius of 1 unit of resolution. So with 1 resolution, or 1 unit of resolution, that is the resolution, then a circle drawn around the middle of the focus cell would only include the middles of the cells that are in the north, south, west, and east directions, the ones highlighted in red here. And so the circle becomes a cross in the sense of a cell. And we automatically have, no way to make it more circular-like because it's using square cells. And so we can't get a perfect circle. And that's why it's not used as often as the square ones are. Although, the larger the circle, the less issue it is. So the larger the circle, so if you have greater than 1 unit of resolution, and here we're talking about linear units, like let's say 30 meters, then it becomes less problematic that it looks that you miss some cells along the corners. And that might be, in many circumstances, very useful. For example, if you're looking at, let's say, a communications tower. Well, a communications tower, its signal, in all other things being equal, would decay, because of atmospheric disturbances, in a isotropic way, and that means decay would be the same in all directions. And so a circle is a good thing to use to model the distance at which a particular signal would still be strong enough to be picked up by a receiver, like a cell phone, for example. So in those cases, circles make sense. The annulus is basically a donut shape. So annulus you can always think of as a donut. And it could just as well be called a donut, but it has to have that more of a Latin-derived name here. So we have 2 radii, an inner radius and an outer radius when creating a annulus or donut shape. All cells in the inner radius are excluded, and all cells between the inner and outer are included. So that's your inclusion zone here. like so. And again, that can be interesting when you're looking at relationships that have a certain functional, you have a certain functional understanding of relationships and how they may change with distance between the focal cell and the cells out here that are further and further away. And you want to know, for example, is there a certain relationship between the focal cell and cells that are this far away and between this far away and that far away, so that you have an inclusion zone here. This is, again, a very specialized one, often used in the context of examining spatial relationships between values, more so than other things. Now, in Python, the neighborhood is a class. This means that there is no physical object that you can see on a map called the neighborhood. The class neighborhood exposes methods or functions that we can use to create or define neighborhoods in the way we want them to be defined for an analysis, like a square neighborhood, a circular, etc. And that class, that neighborhood class, exposes methods. For example, NBR and nullis would create a donut neighborhood. NBR circle for a circular, rectangle to make a rectangular neighborhood, wedge neighborhood, NBR irregular or weighted. Excuse me. We won't be looking at irregular ones, but those require a file with lines in it that specify the weights of the cells. So generally, if it's unweighted, it would be 0 and 1, so I might have a file that has something like this in it. So this is the file space, like in Notepad, and I might have a 1, 0, 1, 0, 1, 0, 1, 0, 1, or something like that. Let's say I wanted to have there are certain combinations of these things that have well-known properties like edge detectors and stuff like that. So if you need to do a certain type of convolution to your image or raster, you can specify a custom neighborhood like that using a kernel file, which is just a text file. So in Python, what we do is we specify a variable, so a var variable, just call it nvar. We say that's going to be equal to one of these things. Most of the time, nbr rectangle. And that's where we specify the size of the rectangle. For example, a 3, 3 neighborhood, units, cell. Because there are two types of units you can specify for the neighborhoods. You should always, most of the time, use cell. Because cell then puts it in units of the resolution. So if you had a resolution, let's say up here, equals 10 meters, and you want to have a odd number of cells, so you want to, let's say you have, let's say a 100 by 100 meter, 100 by 100 meter neighborhood, approximately. Well, then you say, okay, I want a 10 by 10. But we see that 10 by 10 is equal to, right, 100. So each cell is 100 square units. Let's say it's meters, 100 square meters. But just 10 cells is 100 meters, right? So 10 cell equals 100 meters. And that would be the, let's say, the width of our neighborhood. And then the height would be also 100 meters. And 10 cells, unfortunately, because they both 10 cells is a even number, that would mean that our focal cell wouldn't be exactly in the center. It would be offset from the center a little bit. Now, it doesn't matter so much in such a large neighborhood that it's slightly offset, because the bias has become smaller the greater the size of the neighborhood. But it would still matter at this. So we couldn't get an exactly 100 by 100 and have a focal cell right in the middle. So instead, we might say 90 by 90. And that means 9 times 10 is 90, so we would want to have 9 cells by 9 cells, and cell as the unit. And that will ensure that we have, it's not exactly a 100-meter one, but it's as close as we can get. Or we could go slightly higher to 11 of them. So we could say 11 by 11, 9 by 9, or 11 by 11. But that ensures a cell at the middle. Of course, the other option there is to use a circle, but again, that will always leave some cells not visited within a neighborhood. So you need to specify usually an odd number for cells, width and height, like 3 by 3, 7 by 7, 9 by 9. 3 by 3 and 9 by 9 are common. You don't see too much 7 by 7s, or anything like that in a general neighborhood function. So using cell units ensures that you can always choose an odd number here, and you just have to, in your head, multiply that by the resolution. So 3, like if I did 3 by 3 and I had a 10-meter resolution, that would be a 30 by 30 meter neighborhood size. So you have to do that in your head. And likewise for the other ones, they have different parameters, that's all. So our neighborhood var could be equal to circle. And then in here it asks for radius. Again, that should be in cell units. So if I want 100 meters, because it's a circle, we're no longer looking at the rectangular issue. So a circle could be should be an odd number of cells. It makes it much easier and less bias. So let's say I wanted a radius of 90 meters, so I put my number of cells here as 9 and units as cell, like so. And then that would be stored in a variable called nvar. And that is a variable that simply defines the properties of a geometric object called the neighborhood. Here are 2 solid examples. So a rectangular one, NBR hood, NBR rectangle, and then 9 by 9 cell units. And again, this little diagram showing the difference between a odd number of cells for the width and height and an even number for the width and height, showing you the processing cell in each one. In the processing cell in the 4x4 is biased, and in the odd is not, because it's right in the center. And we could also do neighborhood circle, I should say. So we say NBR circle, 2 cells from the focal cell, and then cell. You see what it looks like here. We have 2 cells, 2 cells, 2 cells, 2 cells, and then along the diagonals, it only gets the inner ones here. So it looks more circular than just a straight up cross, and that would become more and more circular looking with a larger and larger number of cells here. And so when undertaking a neighborhood focal function, first thing you do is define the neighborhood.